Okay, now that we understand, hopefully, keto to enol tautomerization, let's go ahead and see how this applies to the functional group we were studying, which is the alkyne. So this is going to specifically entail looking at the hydration of alkynes. So in a typical alkene reaction, if we had like some R group on our alkene, we would add H plus followed by H2O. So what that mechanism sort of looked like was, well, we could have the pi bond directly attack, or we could consider a resonance structure of the pi bond that put electrons at the less substituted position. In either case, we would prefer adding the acidic hydrogen to the less substituted position so that the nucleophile, in this case, which was water, the lone pair could engage the more substituted position, which is the more stable carbocation because it's more substituted. Okay. So after the water adds, we would then have this intermediate structure, which can lose hydrogen atoms, a hydrogen atom, excuse me, to give a neutral molecule. And that allows us to see how we get H2O, or a hydrated alkene. So this reaction follows the Markovnikov rule. Okay, so we have our alkyne version of this reaction, which has similar characteristics. That is, we could have an unsubstituted, or excuse me, one side being unsubstituted alkyne, and I'm going to put a title in here: hydration of alkynes. And so what we could consider, sure, is a resonance structure, still linear, where we have a negative charge on one side and a positive charge on the other side. So when we add that to H plus, we get the hydrogen going to one side, which is the less substituted position. At this point, we have now an sp hybridized, what's called vinyl carbocation, at the internal position, more substituted because it's the only one with one substituent, which can then react with water. So that carbocation will now be reactive with water, definitely very highly reactive, to give rise to this structure. I'm running out of space, sorry. Let's go ahead and just redraw that up here. So just redrawing the exact same structure. Now we're sp2 at both places, and we can lose a hydrogen atom on the oxygen atom that was once part of water. And it doesn't matter which side I add. Whoop, I don't know why I drew hydrogen still. It doesn't matter which side I put the oxygen atom on. And you might think, well, maybe it does matter. It doesn't. Okay, it doesn't in any case. We get both products, if we could stop here, in a disubstituted alkyne. Okay, but this doesn't matter. Now, you'll see in a second. What typically happens for alkynes is we treat these as two alkene systems. So we do one reaction like it's an alkene, and then we do another reaction like it's an alkene, and we add a bunch of bromines and hydrogens onto the carbons that were part of the alkyne system. That's not the case now. At this point, hopefully the alarm's going off in your head and you're recognizing that this is, in fact, an enol. It's an enol across these atoms. So before another H plus can come in to allow for another water molecule to come in, we're going to let the, it turns out the H plus is actually going to kick us into gear to do the tautomerization reaction. Now, it is true that if somebody's watching this, they're going to say, well, you could form hydrates and you could get the net result of adding two waters onto the molecule. But at the end of the day, the equilibrium, after removing everything and observing our final product, will not be the hydrate of a ketone, it will be, in this case, the ketone. But for my students, in Chem 214, we've done the tautomerization reaction under these hydration conditions. Okay, so tautomerization beats this kind of dihydration reaction that could occur. So tautomerization intercepts the enol to form a ketone. There's no dihydration. So this is why we took a break from alkyne chemistry in the last lecture to look at keto to enol tautomerization. And that's because when we try to do a hydration reaction of an alkyne, we don't see the alkyne behaving as two alkenes. Instead, what we do is we see this first pi bond give way to an enol intermediate that ultimately forms our keto product. Now, this is still, reaction still follows, the reaction still follows the Markovnikov rule. Because the carbonyl CO bond forms at the more substituted, or at what was the more substituted alkyne C atom. So the more substituted alkyne carbon atom is what ultimately gets replaced with the carbonyl. And then the hydrogen ended up, actually both hydrogens of our water molecule ended up at the less substituted position. Here's another example though. If I gave you an alkyne with substituents on either side and they were different, it's not really a fair question. If I wanted to put things on both sides, I would want to make them the same. So that would be a case like 2-butyne. So I could react that with H2O in the presence of H2SO4 as a catalyst. I won't go through the mechanism, but you could draw this or this. They're the same product because we have a methyl group on either side of the alkyne carbons, 4 carbons total. So there's in the product, there's an ethyl group on one side and a methyl group on the other side, and it's the same product in either case. Okay. So we've done the hydration reaction for an alkyne. It follows the Markovnikov rule, but instead of doing a dihydration and putting 2 H2Os on, we do a tautomerization at the midpoint of the reaction to give rise to a carbonyl product where the carbonyl oxygen is at the more substituted position if that is applicable for our scenario. We've talked a lot about the Markovnikov rule. It's pretty useful. It's definitely helpful in predicting which spot or region we get reactions to occur. We call that the regioselectivity. We can actually violate the Markovnikov rule in some selective cases to give exclusively the, quote, anti-Markovnikov product. And the reaction I want to talk about is the anti-Markovnikov hydration reaction, hydration of alkynes. Okay, so anti-Markovnikov, what this means is we add H to more substituted and nucleophile to the less substituted. We're just doing the opposite of what the Markovnikov rule says to do. That is to say, if we have H and a nucleophile being added, instead of H going to less substituted, nucleophile going to more substituted, we're going to flip that and get the opposite. So flip it and we get the anti-Markovnikov product. So what does that look like? Well, the specific reaction that we're going to use is the hydroboration reaction. And it's a hydroboration oxidation reaction of alkynes. So first of all, This is a two-step procedure. Step one is hydroboration. I know we don't know what that is, but we've at least mentioned it at this point. So step one is hydroboration. Step two is oxidation. What I want you to know is the mechanism for hydroboration. It turns out it's very easy. It's pretty chill, but it's really helpful to understanding how this reaction actually works. For oxidation, we'll have no mechanism. So mechanism for hydroboration, no mechanism for the oxidation steps in the hydroboration oxidation sequence. Okay, so what does this reaction look like? Well, if we have an unsymmetric alkyne with an R group, 2 carbons, and then carbon 2 in this numbering system has a hydrogen attached to it, we are going to do a two-step procedure where in the first step we add BH3, and in the second step we add NaOH and H2O2, sodium hydroxide and hydrogen peroxide. The outcome after these two steps is a carbonyl. Typically, it's an aldehyde. And our two hydrogens from the antimarkovnikov hydration have been added to the what was carbon 1, the more substituted position, and the oxygen bound by added carbon-oxygen double bond is at the less substituted position. So that's where we get antimarkovnikov hydration. Okay, so the mechanism for step one only is we first do the hydroboration. In hydroboration, we add a molecule called borane or something like it that has a B and an H atom, and the B is part of a group 3, is in the +3 oxidation state, just the typical oxidation state of borane. So let's go ahead and consider this. And again, not a hard mechanism in terms of the number of curly arrows. So what we're going to do is we're going to take H and B of BH3, and I'll add the other two H's right here. And we're going to go zoom in on this. We're going to take the hydrogen boron bond down to form a bond between the more substituted position of our alkyne and the hydrogen atom of our BH3. And then one of the weakest pi bond is going to be added to the boron atom. And so what we do is we add our B and our H simultaneously to form an alkene that has boron with 2 hydrogens, and these 2 hydrogens could be other things. So this applies if somebody's worried about, well, what if I've got carbons instead of hydrogens for the other 2 spots? As long as you've got 1 hydrogen, it will get added to our alkyne, and that's all we need. That's it. That's step 1. Now, step 2 is the oxidation procedure. In step 2, we're going to oxidize, and I like to write an O with brackets around it to indicate oxidation. In step 2, we're going to treat the boron with some sodium hydroxide and hydrogen peroxide that will oxidize the carbon-boron bond to make a carbon-oxygen bond, and that carbon-oxygen bond is going to simply be an alcohol. But now this isn't your run-of-the-mill alcohol, this is an enol. And enols undergo tautomerization to form ketones, and the equilibrium generally favors the carbonyl form. Okay, so let's take some notes over this. In step 1, a carbon-boron bond forms at the less substituted carbon atom. I was a little focused on the curly arrows, and I didn't emphasize this point, but I need to highlight this to make sure I don't forget this. When boron adds to an alkyne, there's a hydrogen that goes on one side and a boron atom that goes on the other side. The boron always goes to the less substituted position. It has a preference for it, and it's highly selective to go to the less substituted position. I could make some bland argument about steric hindrance and boron being more sensitive to steric hindrance. Probably sufficient accuracy in that statement to warrant it. I'm just not going to, because I think there's a little bit more to it than that. But the outcome is what you should pay attention to. The boron goes to the less substituted carbon, and that's true of any hydroboration oxidation sequence, as we're going to look at this in the reaction of alkenes in a subsequent lecture. But that gave rise to an enol intermediate after oxidation. So what's happening during oxidation? In step 2, HOOH, which is hydrogen peroxide, and NaOH convert Cb into COH. And we don't have to worry about a mechanism for that. We could draw some things that are interesting, but it's just there's enough there that's kind of uncertain. And when I ask you to know mechanisms, it's because there's good reason to kind of be aware. Things have been studied so deeply that there's a lot of consensus around the mechanism, and there's not too many missing steps. And so usually I ask you to know mechanisms when it's helpful in the long run. So here's not necessarily a case, but that first step, just seeing the simultaneous formation of a carbon hydrogen and a carbon boron bond, that's pretty helpful actually. And so anyway, that's the reaction. So you could even say that there's a step 3 to this. Step 3 is tautomerization to a carbonyl, which is often an aldehyde. But if there's substitution on either side, it's no problem. It's just the boron, if it has a choice, it's going to go to the less substituted position. But if you took something like this with equal substitution, and I don't want to mix substitutions, like I don't want to have a cyclohexyl and a methyl because we get both products formed. But if I've got symmetry across my alkyne, I could do the 2-step sequence where step 1 is BH3 and step 2 is H2O2, hydrogen peroxide, along with sodium hydroxide to give rise to a carbonyl. And I could have the carbonyl on either side. It doesn't matter, we get the exact same outcome. Just because there is substitution on either side does not mean the boron won't react. It's just it's more likely to prefer reaction at the less substituted position when it has a chance to. Now you might say, is this really hydration? We didn't add HOH to the reaction at all. I mean, I'm guessing water comes along for the ride with hydrogen peroxide and sodium hydroxide. We would call this a net or a formal hydration. That is the overall change to the molecule. Overall, we added OH and H to the alkyne. The important thing isn't the name hydration. You could call this hydroboration oxidation and never call it hydration. But the important point is that this allows us to achieve an antimarkovnikov selectivity. That is, we can override the Markovnikov selectivity in the event that we want an aldehyde. If we want a ketone, then let's just go with the standard conditions. Or if we have substitution on either side, maybe just go with standard conditions unless there's something that's sensitive to acid that we, enough so that we don't want to actually add acid to our reaction. But anyway, that'll do it for the hydration of alkynes, taking advantage of keto to enol tautomerization.